13 people watching. No, this is good. Okay, so let's. Hey, Maggie. So this is. We'll go over just the history of the atmosphere with you. I think this is where we left off last time, right after sort of like the carbon dioxide as the greenhouse gas. And I know I got some questions about Boyles law. Maybe we'll touch on a little bit of the Boyles law today, but if we don't, we can reconvene tomorrow and just go over the gas laws itself, because I think the gas laws, you just have to look at all three of them all together. It's not as bad as you think, and I'll show you like a demonstration online, obviously, about that. Okay, so like all this is this air pressure, atmosphere pressure. Like we have to think about the progression of this, right? Anytime we talk about science, science, like all the discoveries didn't just happen in one day or one person. It's the building pieces of pressure, really, right? So if you think about even the COVID-19, the coronavirus, right? Like if when they I'm going to say when they find or develop a vaccine or know more information about that, it's going to be researchers from around the world, different scientists figure out the little pieces of the puzzle, and then eventually coming up with developing the vaccine or a cure for all of this, right? Just same for atmospheric pressure, because if you think about before, people didn't realize that air actually weighed anything, right? Because it's invisible, right? A lot of times we only think things exist because we can see it, but we can't see air. We can't really see the effects of air, right? We can't see the effects of our air pressure or atmosphere pressure. So how did people figure this out? So if you look at the key sort of players, so if you look at your work booklets, I have those different profile cards. Basically, it's just like a summary of you jotting down the name, the contributions to this entire sort of story. Obviously, there's going to be other people involved with this, but these are the main characters. And it's just like a summary sheet for you. You want to get down, Penny? Okay, you can stay there. So one person obviously is Galileo. You probably have heard of Galileo before. Galileo Galilei. It's this is all. If you look at the dates, it's in the 1500s, 16th century, and then Torricelli, Boyle, Otto von Guericke, Blaise Pascal, which you probably recognize, and Charles's, which is the Charles's law. So if you look at all these people, they play a big part of developing all those laws, because you can recognize like there's Boyles and Charles, even Gay-Lussac. I don't know why he was left out in here. I don't know why, but that's kind of strange. But all these people contributed to the sort of looking at the variables involving with air pressure, and then mathematically developing a formula to look at it, right? Like that's the key. That's the important part about the science, is that there's the mathematical relationship between these variables. It's not just like this goes up, this goes down, but there's a relationship. So back in the day, if we were to look at the history of this, in the late 1500s, there's mining industry, and in order to sort of get to the ore, they have to dig deep into the ground, right? And water had to be pumped out of the shafts, and to prevent seepage. So if you look at this, is an old picture of this. This is in a mine, and these are different sort of pumps to pump the water out. So you can see that it's like a sequence of pumps, and the challenge at that point is that the pumps actually can't lift the water more than 34 feet. So if you look back at this picture, if you have a pump that exceeds 34 feet, that water actually just can't be pumped out. It doesn't matter how much. You want to get some paper? You okay? Did you get a scratch? How did you get a scratch? Oh, okay. Do you need a band-aid? Yeah? You want to go ask mommy for a band-aid? Yeah? So, the pleasures of live streaming, right? So like you can see that the pumps can't lift water more than 34 feet. So then they had to use series of pumps, but people didn't know why water can't be pumped over 34 feet, because it was just like, okay, once it exceeded 34 feet, we just needed another pump. So this was when Galileo came, and Galileo did a lot of things and had tons of discoveries, and eventually he was put on house arrest for his sort of heliocentric model of our galaxy or or solar system, right? And he had some credit because he came up with these ideas. He tried to figure this out as well, and then he raised this question, and it wasn't until his assistant Torricelli, also near in the same sort of timeline, he developed experiments to sort of mimic this, right? But since 34 feet, if you think about 34 feet, is quite long, so it's hard to sort of develop an experiment with 34 feet of sort of tubing. He used mercury, because instead of using water, he used something that was heavier than water to show that. And he used mercury because mercury is about 14 times heavier than water. And so instead of having 34 feet, he's going to use something that's heavier, so then he could shrink his experiment, which is why he used mercury. And he was really the first to develop the barometer to look at air pressure. And what he did was basically he just filled a glass. You probably have done this in a bath when you're little anyways, because you fill your glass, this tube, with, for his sake, he used mercury, and he inverted it and put it into a bowl of mercury as well. Just like if you were to take a cup, right, fill this with water, and then invert it into a bowl of water, you can see that that the water doesn't come out, right? That's the thing. That's really his experiment. And what he did, though, he sort of recorded this mercury. So did it go up or down depending on the day, and also depending on the weather, because different weather patterns will provide different, because it's due to air pressure, can actually affect how high this is, right? So if you were to look at this, what he did was that he had this tube, filled it with mercury, inverted it, and this height of mercury is really the sort of the pressure, the air pressure. So how does this make sense? What's the air pressure here? Well, when this inverts, right, this mercury is heavy, so it's going to sink down. But how come it doesn't sink down all the way? So you have to remember that there's air particles, right? In our atmosphere, there's air particles that's going to be sitting on here, right? So all these air particles that's going to be sitting on here, once this has sort of reached the equilibrium, that it's not going to go down or up, the amount of pressure that this is pushing down is going to be the same as the air pressure that's sitting onto this bowl of mercury, right? And because of that, at sea level, this height is going to be the standard. And it actually turns out from here to there, it's going to be 760 millimeters of mercury. So when you're doing your questions, some of you might actually have read ahead about this, or looking at the standard units for pressure. 760 millimeters is really this height, 760 millimeters. That's at sea level. If we were to take this up a mountain, I think I clicked the wrong button. If we were to take this up the mountain where the air pressure is a lot less, that means there's less air particles sitting here. That means that this mercury is going to go push down a little bit further, right? Because there's less air molecules sitting on here. So because of that, your air pressure is going to drop. So then instead of having 760 going up, you might have 700 millimeters or 500, depending how high you are in the atmosphere. All right, so that's really the first barometer to look at the air pressure. Pretty interesting. So here's a short video about how barometers work. I don't know if you guys have sounds on this. Can you let me know if you have sound? I'm not sure.
Aristotle famously said, "Nature fears of empty space," when he claimed that a true vacuum, a space devoid of matter, could not exist because the surrounding matter would immediately fill it. Fortunately, he turned out to be wrong. A vacuum is a key component of the barometer, an instrument for measuring air pressure. And because air pressure correlates to temperature, and rapid shifts in it can contribute to hurricanes, tornadoes, and other extreme weather events, a barometer is one of the most essential tools for weather forecasters and scientists alike. How does a barometer work, and how was it invented? Well, it took a while. Because the theory of Aristotle and other ancient philosophers regarding the impossibility of a vacuum seemed to hold true in everyday life, Few seriously thought to question it for nearly 2,000 years, until necessity raised the issue. In the early 17th century, Italian miners faced a serious problem when they found that their pumps could not raise water more than 10.3 meters high. Some scientists of the time, including one Galileo Galilei, proposed that sucking air out of the pipe was what made water rise to replace the void, but that its force was limited and could lift no more than 10.3 meters of water. However, the idea of a vacuum existing at all was still considered controversial, and the excitement over Galileo's unorthodox theory led Gasparo Berti to conduct a simple but brilliant experiment to demonstrate that it was possible. A long tube was filled with water and placed standing in a shallow pool with both ends plugged. The bottom end of the tube was then opened and water poured out into the basin until the level of the water remaining in the tube was 10.3 meters. With a gap remaining at the top and no air having entered the tube, Berti had succeeded in directly creating a stable vacuum. But even though the possibility of a vacuum had been demonstrated, not everyone was satisfied with Galileo's idea that this empty void was exerting some mysterious yet finite force on the water. Evangelista Torricelli, Galileo's young pupil and friend, decided to look at the problem from a different angle. Instead of focusing on the empty space inside the tube, he asked himself what else could be influencing the water. Because the only thing in contact with the water was the air surrounding the pool, he believed the pressure from this air could be the only thing preventing the water level in the tube from dropping further. He realized that the experiment was not only a tool to create a vacuum, but operated as a balance between the atmospheric pressure on the water outside the tube and the pressure from the water column inside the tube. The water level in the tube decreases until the two pressures are equal, which just happens to be when the water is at 10.3 meters. This idea was not easily accepted, as Galileo and others had traditionally thought that atmospheric air has no weight and exerts no pressure. Torricelli decided to repeat Berti's experiment with mercury instead of water. Because mercury was denser, it fell farther than the water, and the mercury column stood only about 76 centimeters tall. Not only did this allow Torricelli to make the instrument much more compact, it supported his idea that weight was the deciding factor. A variation on the experiment used two tubes, with one having a large bubble at the top. If Galileo's interpretation had been correct, the bigger vacuum in the second tube should have exerted more suction and lifted the mercury higher, but the level in both tubes was the same. The ultimate support for Torricelli's theory came via Blaise Pascal, who had such a mercury tube taken up a mountain and showed that the mercury level dropped as the atmospheric pressure decreased with altitude. Mercury barometers based on Torricelli's original model remained one of the most common ways to measure atmospheric pressure until 2007, when restrictions on the use of mercury due to its toxicity led to them no longer being produced in Europe. Nevertheless, Torricelli's invention, born of the willingness to question long-accepted dogmas about vacuums and the weight of air, is an outstanding example of how thinking outside of the box, or the tube, can have a heavy impact.
There you go. See, that's a really great video about that. So that's really how your barometer works. And then again, like this is what Torricelli did. I don't think I need to kind of go into this in detail again, but like he used different kinds and still observed the same height. And I think I have tons of pictures. Here's one. So like for development, so this is a very interesting one. This is Otto von Guericke. So he used that idea and he actually made a pump that created the vacuum. So let me see if I can move this over. Made a vacuum so strong that a team of 16 horses couldn't pull the metal spheres apart. And so if you think about this, it's basically there's a vacuum, take the air out from these two sort of hemispheres, and then 16 horses couldn't pull that apart. So this is a diagram of this. I found a YouTube video which is showing us this happening. And the thing is that actually doesn't have... it's not in English, but I'll show this to you, and it's pretty interesting that somebody has tried to replicate this this experiment. And I'm just gonna mute this. But like, so this is the hemisphere, and they're taking the air out. So it's just like, remember, like when we look at the bell jar in our classroom with the vacuum, right? So if you take the air out, instead of having glass, that this is, I think it's a pretty sturdy sort of two hemispheres, and they're going to try to pry this apart. And this is pretty interesting. This is all due to the air pressure. It's nothing glued together. They're not gluing things together. They're not like drilled on. This is just air pressure that's making this work, right? That's pretty interesting. So if you look at this, there's two tractors here, right? And they can't pull this apart, and this is all due to air pressure, right? Abby, did you see that? Look at this. They can't pull that apart. It's just all air pressure. Oh, finally they did. But like, you have two tractors pulling this together. It's so cool, right? So that's all due to air pressure. So pretty neat. Let's just kind of finish off here. Any questions at this point? Blaise Pascal took the barometer up and down the mountain, just like in the video, and you notice that when you look at the standard units of pressure, there's like Pascal, that's really from Blaise Pascal. There is also a unit called Torr, which is for Torricelli, and the kilopascal is just 1,000 Pascal, just to make it smaller unit. But that's really the history of pressure. And Torricelli has this sort of famous quote saying, "We live submerged at the bottom of an ocean of elementary air, which is known by incontestable experiments to have weight." So very elegant, looking at how that we are actually submerged in this ocean of air. So that's the story of pressure. Any questions about that? Let me know. I'm gonna move on to other things. So if you want to type in your question, I hope this is still working. We're all good so far. Hey. See, Abby, do you see all these people, these names? See, those are my students. So they're watching me, so they can see right now too. You want to wave? No. You want to wave? Okay. So let me just kind of quickly go into the gas laws, or looking at this, the unit measurements of pressure. So here's this notes to all of these ones. Let me see if I can kind of highlight this. There are different ways of measuring pressure. So one is atmosphere, and one is kilopascal, kPa. Millimeters of mercury, so you know where that's from, millibars and pounds per square inch. But if we were to look at sort of the measurements of atmospheric pressure, it's usually the atmosphere kilopascals or millimeters of mercury. And you need to know how to convert these. And if you watch the unit analysis way, that is a really, really useful way to convert anything. I know you probably have done this in math, and like converting millimeters to kilometers is either calculator work, or I mean, like you can use your phone, but like this way will help you. Like this unit conversion way will help you, not just for this unit, but moving forward when we look at moles and all that. So one thing you need to know, I shouldn't say you need to know, this is all going to be given to you. So these are all of your conversion factors that you're provided with, and how you want to convert is like this. So let's say that I'm just going to do it here, since the conversion factors are here. And if we were to convert something like, hey, you have 630 millimeters of mercury, right? How you want to use this unit analysis way is this. Whatever you want to convert, that's what you start off with, and then you're going to do a times division bar. This times division bar is looking at the units now. So the whole purpose of this unit analysis is looking at how the unit that you start off with is going to disappear, and how you're going to get the new unit. So if we were to convert this to say like kPa, right? What you want to do is that you want to get rid of this unit. You're going to put that at the bottom. So millimeters of mercury is going to go to the bottom. And then what you want is going to go to the top. So this is your kPa. After you have all of that set up, then you're going to put your conversion factors, so you know that all of these are equivalent to each other. So 1 atmosphere is the same as 760 millimeters of mercury, which is also the same as 14.7 psi, same for 1.1, etc., etc. So I'm going to put 101.3 divided by 760 millimeters of mercury. And the math here is that the millimeters of mercury are going to cancel out. So what you're going to do is 630 times this divided by that. So millimeters of mercury will cancel out. This becomes your new unit. Okay, so this is going to be your kPa, is your new unit. And whatever math you have is your number. So let me kind of punch this in. I can't do that in my head. So I'm going to punch 630 times 101.3 divided by 760. And I'm going to get 83.97. So this 83.97 is exactly the same as 630 millimeters of mercury, just in a different unit of measurement. That's how you want to convert. Okay, so the setup is really that whatever you want to get rid of is going to be at the bottom of the denominator, and whatever you want is going to be at the top. Okay. So you want to try some of these. I know there's a couple sheets in your work booklet that's about conversion, and give those a try. Okay, so moving on to gas laws. Gas laws is really just 3 laws: Boyles law, Charles law, and Gay-Lussac's law. One really good animation is this. Let me see if I can show this to you. This is, let me see, open this up. Oh, put this on the screen. Let's see if we can make this a little bit bigger. And if you look, this one doesn't have any sound too, but it's looking at gases, right? So remember when we talked about the kinetic molecular theory about particles moving straight line, bumping into each other. It can exert pressure. If you have a lot of energy, they're going to excite each other. They're going to move faster, which they can push and exert pressure more. If you cool it down, they can contract, move a little bit less, right? That's why we studied the KMT in the beginning. This one, if you look at, let's see if I can talk about this. This is inside the balloon, so there's gases inside the balloon, and as you heat it up, inflates, the volume will go up. That's why it gets inflated, right? Because you're adding more gas particles. So then this is, right now, if you think about a balloon, there's a couple variables that would affect the size of it, right? So increasing the temperature will increase the volume, right? It will increase the size. You know that, right? Also, if you were to increase in, like if you keep increasing, eventually it's going to explode, right? That's like one gas law right there. Increase in temperature, increase in volume. What happens if you were to put this in a vacuum? So this is the bell jar, right? You're taking, right? When we turn the vacuum on, we're taking the air outside of the balloon away. So what's going to happen? Why does the balloon expand? Well, this is going to show you. This is actually really good animation, right? Vacuum turns on, gas disappears. So the gas molecules inside the balloon can exert more pressure because there's no pressure on the outside pushing against it. So that's why the air molecules inside are exerting pressure, pushes the balloon bigger, right? And expands. So this is really another gas law. Like if we were to look at the gas laws, don't think about it as 3 separate laws. I mean, like there are 3 separate laws because there's 3 sort of independent relationship, but all those variables are actually happening all at the same time, right? Your pressure, your temperature, and your volume. So this one is looking at that if we were to decrease the pressure, right? We take those molecules out, the volume goes up. Why is that? Well, because you have less pressure exerting, pushing against the balloon, and then the balloon inside can push out a lot easier, making the balloon expand, just like what we've seen with the vacuum. Eventually it pops for this one. And then the last one here is that, let's see what's the next one. This is gas inside the bell jar. So if you were to, say, increase the temperature, well, how does that relate to KMT? Increase in temperature, increase in energy, molecules move faster. When molecules move faster, they're going to push against each other harder, against the walls harder, which means increase in pressure, right? That's why it's so important to understand the KMT and using those correct vocabulary, all right? So we won't look at Avogadro's law because that includes your moles here. We won't look at that. But this is your three laws, Boyles, Charles, and Gay-Lussac's, and they're really just looking at pressure, volume, and temperature and how they relate to gases, and that's it. So that's a really good animation. So I left it on your OneNote, so give it a check that out. Yeah, so if we were to look at I can just bypass all this stuff. I think this is just looking at that's what we talked about. One important part here is that there's some questions that's asking you like what happens at standard temperature pressure. So this is the standard temperature pressure of the gases. And when things are set at STP, at standard temperature and pressure, it means that it is at 0 degrees Celsius, which means it's at 273 Kelvin. We'll look at the Kelvin once we get into the Charles's law. And then this is your pressure. So your standard pressure is at 101.3 kPa, or 1 atmosphere, or 760 millimeters of mercury, or 760 torr, or 14.7 psi. All of those ones you don't need to memorize. Those are all given to you, but you need to be aware that those ones are your standard temperature or pressure. Okay, 0 degrees at those pressure. Okay, so this is your three gas laws: Boyles, Charles, and Gay-Lussac's. And Boyles' law is all about the pressure and volume. So if you look at the mathematical relationship, it is looking at pressure and volume and how they relate to each other. So if you think about, if you were to grab a balloon, if you increase in pressure, how will that affect your volume? If you were to squeeze the balloon, will your balloon get bigger or smaller? Well, you know that if you squeeze a balloon, it's gonna decrease the volume. So this is an inverse relationship. So whatever increase pressure you have, your volume is going to decrease. So this is an inverse relationship. Any questions? If you have any questions, just type them up, or even just say something on the chat so I know you're still there. All right. We're good. I think we're okay. So the unique thing about any of these laws is that those relationships are mathematical. That means that they're proportional to each other. That means that if you increase your pressure 2 times, your volume is going to decrease 2 times. If you're to squeeze 4 times as much, your volume is going to increase 4 times as much. So that's the unique thing about this, is that they're proportional. Okay, and if you were to look at the graph in a relationship graph, in a linear relationship, right, it is actually like this. That means that if you increase this much, it's going to decrease the volume the same amount. Okay, and that's really it. If you were to do a question, right, here is a sample question. A balloon contains 30 liters of helium gas at 103 kPa. What is the volume of helium when the balloon rises to an altitude where you only have this? So one really good way to set this up is to write out what you know. And if you look at this, you have a volume and you have a pressure. So I would say that this is my V1 and that's my P1. So my first volume is going to be 30.0 liters, and the next one is going to be 103 kPa. And then the next one is, what is the volume of the helium? So what is the final volume? You can say V2 or VF, up to you. And then it rises to an altitude where the pressure is only 25 kPa. So if you look at this, this is my setup. And then you can put this into your formula, right? So your formula is PV is equal to PV. And then this is going to be 1, 1, 2, 2. And then substitute all this. So this is going to be, oh man, how do I erase this? Here's my eraser. So this is going to be 103 times 30 is equal to 25 times V2. And then solve for V2. So I want to isolate V2. I think you all are pretty good with this. So divide by 25 to both sides. Cancel. And then V2 is going to be, hey, the answer's right there. 1.24 times 10 to the 2 liters. Don't forget your units. Yeah, so this is in scientific notation, or it's just 124 liters. So that's your Boyles law, right? I think the math part for gas laws is pretty straightforward, because I think people tend to enjoy this unit because people tend to raise the marks, because the math, I think, is pretty straightforward, especially if you've taken pre-calc. Don't forget the concepts, the conceptual part, which is always the tricky part, right? Explaining. So one simulation that I posted on OneNote is this one, which is very useful, is that you can even just kind of play around with this. So go to explore, and this is how this works. You have this closed container. You can always open or expand, and then this is the pump to pump sort of the molecules in. So as you see, as I pump it, the pressure goes up, right? So then you can look at this. You can actually trace the data here. Is that if you were to pump this right now, it's at 33.7 atmosphere. It's pretty consistent, right? Because it's closed, right? The pressure is the same. So then if I were to, let's say, close the volume of this, right? If I were to make this smaller, you notice that the pressure increases, right? The pressure increases because Boyle's law is that if I were to decrease the volume, my pressure increases. It makes sense, right? The thing is, like, the mathematical, you can actually collect these numbers and graph it, and you see that there is a relationship, an inverse relationship. If I were to open this, make this to have a more volume, right, more space, you can see that my pressure will drop. You can also, like, if you want to extend this a little bit further, what if I were to heat this up, add some fire? You notice my temperature goes up, right? But also my pressure went up as well. Look at the pressure goes up, right? If I were to cool this down, all the way, right? Right now the temperature is at, let's change this to Celsius for now. If I were to cool this off all the way to negative, let's see how cold we can get, right? You can see the molecules are slowing down, and eventually we're going to reach absolute zero. That's when there's no movement at all, and that's it, right? So when is it absolute zero in Celsius? It's at negative 273 degrees. Even right now, like, the molecules are not even moving. Like, the pressure is so low, it's at 0.4 atmosphere. So let's change this to Kelvin, right? Let's see if we can get to 0. This is 2, and then eventually this is at 1 Kelvin, and then once we, oh, there's 0, no pressure. Let's see what happens if we were to open it. Nothing, because it's still so cold, right? And if we were to push this together, oh look, the temperature went up because our volume dropped and pressure increases. So that's a really good, just to play around with this, just to test your understanding. But that's all I wanted to do today, just to go over the Boyles law. I don't know if you have any questions about this. I can open up the work booklet, but I would say, you are all good. Well, look at this, man. We're done all this stuff. Let's see, Unit 1. If you have any questions or anything, comments, type them right now. Let me see if the live chat is working. I don't even know if the live chat's working because there's no one saying anything. Let's see. Bypass this, we finish this. Okay, so like this, worksheet number 1, this is practice your pressure unit conversion. This is using your unit analysis method. Just make sure you know how to convert this using that correct method for sure. This is just to it's just like a summary for what all of the scientists did. If you want to draw a picture, go right ahead. You don't have to. This is just to as a summary. So the first one is Boyle's law. So this is below 3 containers. I just realized I didn't draw the 3 pistons. So if you were to have a piston that looks like this, and then let's see if you were to have a piston that is a little bit smaller, right? And then even one that is a little bit more narrow. Oh, that's not a straight line, so we can do that again right here. So if you were to draw 5 molecules in each of those ones. What would they look like in each of these ones, right? That's what I wanted to do. And then if you want to graph the relationship between pressure and volume, that'll be great. And then here's some calculation questions. And that's it. So hopefully you guys all took a picture of the answer key. We can go over some of the questions right here. But, oh, totally, my screen is not even on the screen. Oh, there we go. Sometimes I forget to look that way. Oh, there we go. And then, there we go. That's a little bit better. Okay, so that's it. I don't know if you have any questions, but if you have any questions, let me know. Take care of yourself. If you have any questions, email me. Take care of each other, and I'll see you another time, maybe tomorrow or Wednesday. But thanks for watching. Like and subscribe. I don't know what else to say. I started a TikTok account, so I started learning some dances with my wife. Anyways, I'll talk to you soon. Bye.